Good morning, everybody. Today we are here to talk about our project, which is for SJM 2013, which is Mechanics of Materials. I am Law Jaya, and my team member is Ambok Pidrovs and Max Hong. So let's come to the introduction part. Mechanics of materials are studies about stress, strain, and deformation under load. Robotics arm need to be both precise and have strength in an industrial application. So in our project here is we are simulating the robotics arm in SolidWorks and also doing manual calculations of it. So for our problem statement is how does our 3 degree of freedoms arm based linkage behave under a 5 kg tip load? So our objective here is to evaluate the stress distribution and measure the tip displacement and calculate the factor of safety. And the methodology here is the stress, which is force per area, and strain, which is the elongation, the little bit increase in length divided by the original length, and also the deformation, which is the changing in the length, which is having the formula of A, the area, times E over F, which is force, and L is the length. And the factor of safety is the stress that is yield and divided by the stress that is allowed.
My name is Max Hong, and today I'll be presenting about the design and simulation of the robotic arm. This section will cover the simplification of the arm design and the analysis done using SolidWorks simulation. For the original design of the arm, is made out of PVC pipes for its linkages, and the joints and power transmission systems have parts made out of ABS. For the syringes and the tubings you see here are the actuator systems for the arm. So to analyze this design, we simplified it by removing the actuator systems, as this syringe and this syringe here on the joints will cause the analysis to be more complex, especially for manual calculation. And the joints are then simplified into a singular block, fixed at the angle of 45 degrees. And as you can see here, this is the original design, and it's simplified down to a much simpler single part version. The dimensions for both of these parts, both of the assembly and the part, are effectively identical. So there will be no significant changes on the design of the arm. And the fixed angle is because we set the angle at like a fixed angle, so it will be easier to perform manual calculations and compare with the simulation later. Here is the drawing for the robotic arm, showing its size and dimension. And on the right here is the cross-sectional area of the PVC pipe. So it has an outer diameter of 20 millimeters and an inner diameter of 16 millimeters. So for the analysis, we apply an external load on the effector hook, which will simulate the weight of a 5 kilogram load. So which will be equal to about 49.05 newtons. And the base of the arm over here is defined as the fixed geometry for the analysis. The types of analysis that we did were for stress, particularly von Mises stress, strain analysis, displacement, and factor of safety. For the stress analysis, it ranges from 3.364 times 10 to the power of negative 2 pascals up to 25.8 megapascals. Most of the highest stresses we can observe are on the sides of the pipes here, As since the maximum stress from the simulation does not exceed the yield stress of rigid PVC, which is around 45 megapascals, we can be assured that the arm will not fail mechanically. As for the strain, it ranges from 1.847 times 10 to the power of negative 11 up to 8.62 times 10 to the power of negative 3. And similar to stress, the strain regions are concentrated around the sides of the pipes here. So from both of these observations, we can conclude that the PVC linkages, especially the first and second one, are undergoing bending, are actually experiencing bending moments. I mean, they're undergoing bending. Yeah. And for the displacement, it ranges from effectively 0 up to 7.466 millimeters. Most of the displacement is occurred on the effector hook here, where the load is being applied. So the difference between the original position and the final position is more obvious in an animation here. And finally, for the factor of safety, we it ranges from 1.74 up to about 290. So for the factor of safety, for the PVC linkages, the factor of safety ranges around 1.74 as they are mostly like red in color, mostly red in color. So from the analysis, what you can conclude is that the arm would not fail mechanically as the maximum stress experienced by the arm does not exceed the yield stress of its material, which is rigid PVC. But another thing to note is that since the effector hook can undergo a displacement of up to 7 millimeters, which is quite significant, it will not be able to perform a task of moving objects around accurately. So to improve the design, what can be done is we increase the outer diameter of the linkages, or we can get a material which is more rigid than PVC, particularly having a higher elastic modulus, so that more stress will be needed to deform the arm.
Assalamualaikum warahmatullahi wabarakatuh and greetings everyone. So I am Muhammad Faiz Imran, and in this assignment I am tasked to conduct the manual calculation analysis for our robotic arm. So in order to analyze our robotic arm, first we have to construct the free body diagram of that particular structure. So now as you can see here, I have initialized the angle between the joints to be 135 degrees respectively on joint B and also joint C. And the angle, the length of pipe AB is 100 millimeters, different from the length of pipe BC and pipe CD, which is 150 millimeters respectively. So only then I will be able to calculate the deformation, normal stress, shear stress, and factor of safety of this particular free body diagram. And also one thing to note here, I have also taken off the fixed support at A. So since it is a fixed support, we have to keep in mind that there is a moment acting at that particular spot, and also there is a reaction force. Now, other than the free body diagram, there are also some other constants that we have to initialize, particularly in this context. Now, some of the constants include elastic modulus, which is 2.41 times 10 to the power of 9 Pascal. And then we have the cross-sectional area. So now the outer radius and also inner radius that I have included inside this cross-sectional area was initialized in the SolidWorks model, and this was covered by Mark Zihong. And then the limit of shear stress and also limit of normal stress. So the limit of shear stress and also normal stress was unfortunately not determined in the SolidWorks model because it was not possible. However, we did a few research and we found out that a structure, which is a PVC pipe, similar to the material that we use in our robotic arm, has the shear stress of 68.948 megapascal and also normal stress of 45 megapascal, the limits of those both stresses. Now, moving on to the free body diagram. After I've taken off member AB from the overall free body diagram, I've determined that there is a normal force acting on it, which is 49.05 Newton. So, as I have known this, it is quite easy for me to calculate the deformation, which turns out to be 18 micrometer, and the allowed normal stress, which is 433.70 kilopascal, and also the factor of safety, which turns out to be 103.76. Now moving on to another member, which is pipe BC. So this particular member is not as easy to calculate, the reaction forces, because as you can see here, the force acting on it cannot be directly observed as a normal or shear force. Instead, it is acting on an axis which is, I would say, vertical, which is a vertical axis. So There is an approach for us to find out the shear force and also normal force for this particular problem. Now, one of the method that I use is the triangle of forces method. So we have already known that the greatest force acting on that particular point, which is point B, is 49.05 Newton. From this, we know that I would say the highest magnitude of a force in a triangle of forces would be the hypotenuse. So the hypotenuse would be 49.05 Newton in this case. So we also have to know the angles between the sides of the triangles, which we already do, which is 45 degrees. So based on these informations, we are able to know the Fx, or the normal force acting on that member on pipe BC, which is 34.68 Newton. And since it's a 45 degrees angle, the shear force turns out to be the same, which is 34.68 Newton also. Now, after I have determined the shear and also normal force, I reconstructed the free body diagram so that it will be easier for me later on in this analysis. So the deformation is the same as for the formula, and the value turns out to be 19.09 micrometer, which is a little more than the previous deformation for pipe AB. Now the normal stress is 306.64 kilopascal. The factor of safety for normal stress is 146.75, and the allowed shear stress is also similar to the allowed normal stress, since it's a 45 degrees angle, so it is natural for it to be similar. And however, the factor of safety is different, as we have initialized the allowed limit for the shear stress is 6.8948 times 10 to the power of 7 Pascal. So the value for the factor of safety for shear stress turns out to be 224.85. Now pipe CD is quite simple, because as you can see here, the force acting on it is downwards 49.05 Newton, and it is a linkage, it is not a fixed support. Therefore, there are only reaction forces acting there. There is no moment. So it is basically the same process. However, one thing to note here, there is no normal force acting on it. Therefore, there is no deformation. Theoretically or numerically, there is no deformation. However, in simulation, this might be a different case, because in theoretical calculation, there is a lot of variables that are kept constant and not influenced by natural causes that we could not detect, that we could only detect in a SolidWorks simulation or other more intricate or more or a simulation that is much closer to real life. So to summarize, the shear stress is basically, the allowed shear stress is basically 433.70 kilopascal, and also the factor of safety is basically 158.98. So with that, I have analyzed all of the members in the overall free body diagram. Thank you.
So in conclusion, for our peak stress, our simulated result is 25.86 megapascal, and compared to the manual calculation, which is 27.1 megapascal. And for the displacement, for the simulated result is 74.7 millimeter, compared to the manual calculation, which is 62 millimeter. And for the factor of safety, it is 1.74 compared to the manual calculation, which is 1.66. So based on this result, we can conclude that the base linkage is safe, but it flexes too much for high precision work. So in order to solve this issue, we have to do the material upgrade, or we have to change the geometric shape of our robotic arm. And that's all from us, and thank you very much.